programs. We items before we start. All attendees will be muted during the webinar. We have disabled the chat feature during this session. However, questions can be sent in the Q&A section at the bottom of your window. We will gather your questions during the webinar and hold a question and answer discussion at the end. We will be reporting AIA credits for those who attend at least 75% of this live webinar. If you have an AIA number and did not give it upon registration, please send it to webinars@stifirestop.com. If you are not a member of AIA, you can use your certificate of attendance to self-report to whichever agency you wish. In addition to your certificates, STI has partnered with Credly to provide you with a digital badge of your credentials. Digital badges can be used in email signatures, digital resumes, and shared on social media sites. And finally, a recording of today's webinar, along with your certificate of attendance, will be uploaded to our Firestop University within the next 5 business days. You can connect to our Firestop University through your Access STI dashboard, which we will tell you about at the end of today's session. Please remain with us until the end of this presentation to receive instructions on how to retrieve your certificate. And now I would like to introduce John Zalepka.
Thank you, Anna. Mass timber materials such as cross-laminated timber, mass plywood panels, and glulam beams and columns are relatively new to construction and are certainly a hot topic. When it comes to fire-stopping mass timber construction, there are often unique challenges because the building itself presents a fuel source for fire. Our presenter today is Tim Maddox, STI's Senior Manager, Engineering Manager, and our resident mass timber guru. And today, Tim's going to discuss some challenges of fire-stopping mass timber construction, highlighting the advancements made in the building codes and how we, as manufacturers, test at independent third-party labs to ensure life safety in these structures. This material is copyrighted material. It's been developed by Specified Technology, so please do not reproduce, redistribute, or display any material without contacting us first. This course has been approved for one learning unit, HSW, with AIA, and as part of the continuing education requirements, here are today's learning objectives. At the end of today's program, you'll be able to identify the different types of mass timber components. You'll be able to locate changes of mass timber code over the last 3 years. You'll be able to recognize that even though it's combustible, there are some unique properties of wood that make it suitable for fire-rated construction. And finally, you'll be able to explain the differences between mass timber and traditional construction fire stop testing. And with that, I'll turn it over to today's presenter, Tim Maddox. The floor is yours.
Thank you, John. I appreciate the introduction and want to welcome you to today's webinar. Today, we'll be discussing fire stopping in mass timber construction. Cross-laminated timber, or CLT, is the most common material used in mass timber projects and was developed in Europe in the early 1990s. The first noted construction project for public use that utilized cross-laminated timber was in 1996 in Austria. The first recognized commercial project in the United States was in 2016. Growth of the industry has surged since then in light of efforts to control atmospheric carbon, and as such, major code changes were proposed for the 2021 IBC, which were adopted significantly, changing the way Type 4 construction is addressed. These code changes prompted a serious amount of attention to be focused on mass timber construction, which had been lacking before. This is especially true as it relates to fire protection, which of course is important to understand as wood is, in fact, naturally combustible. Our conversation will begin with an overview of different types of mass timber materials used in mass timber construction today. From there, we will talk about the sheer size of some of the projects that have been built, as well as those that are being planned for the future. Next, we will talk about code changes that happened between 2018 and 2021 in the IBC that significantly changed the landscape of mass timber structure allowances and the wood surface visual exposure limitations for each Type 4 group. Then we will talk a bit about wood as a fire-resistant construction material and how fire resistance is calculated. Basically, or because we are talking about visually exposed solid wood construction, it is important to understand how wood behaves in various exposures and why. In this section, we will also show some fire tests that we've performed at STI and some of the lessons we've learned about the nuances of fire stop testing in solid mass timber assemblies. We will close the presentation with a discussion what changes you will see with design listings, and how to recognize CLT floor and wall listings that you well before wrapping it up with some conclusions. So let's start by asking a question: why do we build with wood? And the first obvious answer to that is that wood is readily available, renewable resource that has very good strength to weight ratio. But we've been building with structures with wood for over 10,000 years, and some ancient structures are still standing today. What we are not talking about here is wood framing. We are not even talking about heavy timber, which is more relevant to the use of heavy rafter beams used commonly in the 19th century construction to produce large covered but open spaces. Rather, we are addressing massive engineered wood members that simultaneously provide the primary structure and the fire-resistant barrier. Mass timber can be, and often is, used in conjunction with heavy steel, but the majority of the visible structure of a mass timber project is wood. How can it be, you might ask, that wood can maintain structural capacity while it's burning? Doesn't it lose its strength as it burns? We will get into that. We build with visually exposed wood because it is beautiful to look at. The concept known as biophilic design is used to create space around us that brings us into touch with nature. It has demonstrated psychological benefits. It makes us feel good inside to be connected with nature. As stated previously, wood is a renewable resource. Where trees are harvested, new seedlings can be planted right behind them. In fact, in 2016, the T3 project in Minneapolis, Minnesota, which is about a 220,000 square foot office space, about 6 stories tall, and at one time was the largest mass timber structure in North America, was constructed in about 9.5 weeks, and the quantity of wood used to construct this project is renewed every 4 minutes at the current harvesting and growth rate. Another benefit of using mass timber is absorption of atmospheric carbon. Once construction is complete, it serves as a natural carbon filter for the lifetime of the building. If you're like me, it was not that long ago when you first heard the term CLT. Maybe the first time you heard it was in the introduction to this presentation. But what most people are unaware of is that there are several more building products on the market that are used in mass timber construction today. It is a bit of an alphabet soup, as all of these products are more commonly referred to by their shortened acronyms: CLT, glulam, NLT, DLT, LVL, LSL, PSL, and MPP can be present on various mass timber projects today, and over the next few slides, I will talk about these different materials and their common uses. Let's start with the most commonly used mass timber product, cross-laminated timber, or CLT. Cross-laminated timber is a subcategory of engineered wood. It is a wood panel product made from gluing layers of solid sawn lumber together. CLT has multiple application orientations and can be used in floors, walls, and roofing. CLT is produced with an odd number of layers. The thinnest CLT is 3-ply. The most common used in construction are 5-ply, 7-ply, and 9-ply. Individual plies can have the same thickness or can be of varying thicknesses and are always placed 90 degrees in fiber orientation on each successive layer. To give perspective on how quickly this industry is growing, I visited a CLT manufacturing plant in Canada last year, and they informed me that their production has increased 7-fold year after year for the past 3 years running. That is not growth, that is an explosion. Mass plywood panels, or MPP, are becoming more common. MPP is a massive, large-scale structural composite lumber-based panel designed as an alternative to concrete and steel, and actually to cross-laminated timber as well. MPP is essentially multi-tiered plywood using thin veneers that are laminated with fiber orientation alternating on each successive layer. Similarly to plywood and CLT, MPP can potentially achieve the same structural attributes of a CLT panel using 20% less wood. Glue-laminated timber, most commonly known as glulam, is very common on all mass timber projects and is made with multiple layers of solid wood lumber bonded together with a high-strength adhesive to form a single structural unit. Glulam is oriented such that the grain of all lamination runs parallel with the length of the member. Applications include straight beams, lintels, purlins, ridge beams, floor beams, and columns. You will also see glulam for round, square, and complex sections, tied rafters, trusses, tied arches, arch supports, and curved beams. Nail laminated timber, or NLT, uses screws to connect dimensional lumber in successive layers. NLT has multiple uses, and one major benefit is that it can be constructed on or off site and is often used to create complex shapes, such as the one shown in this photo on the right, as opposed to the straight sections you would normally find with other mass timber materials. Dowel laminated timber, or DLT, is all wood construction using dowels instead of screws and adhesives to connect dimensional lumber. DLT is the only all wood mass timber product using no metal fasteners or adhesives. DLT can be used in multiple orientations. Here it is being used as a roof assembly. A different form of mass timber product altogether is structural composite lumber in the SCL or SCL. Parallel strand lumber, or PSL, is manufactured from veneers clipped into long strands, laid in parallel formation, and bonded together with an adhesive to form the finished structural section. It is commonly used for beam and header applications where high bending strength is needed. PSL is also frequently used as load-bearing columns. Similar to PSL, laminated strand lumber, or LSL, is made from flaked wood strands and is used in a variety of applications from studs to millwork components. Also part of the structural composite lumber family, laminated veneer lumber, or LVL, is widely used structural composite lumber product. It is produced by bonding thin wood veneers together in a large billet so that the grain of all veneers is parallel to the long direction. LVL is a bit of a cross between mass plywood panels and glulam. It is similar to MPP in that it uses thin veneers adhered and pressed together. Although because it is commonly used as a structural member, the wood grain is always oriented parallel to the long dimension of the structural unit, and in that way, it is similar to glulam. These photos are from the Java project located at 1265 Borregas Avenue in Sunnyvale, California. This is a Google office building that was the first of what will be several mass timber structures for Google. For 1980s console gaming enthusiasts, the site location where this project stands today was formerly occupied by Atari. Speaking of gaming enthusiasts, here's a fun memory. In the movie War Games, David Lightman tried to access a video game company server so he could hack into the new games before they were released. This fictitious company was Protovision, located in Sunnyvale. I was fortunate to walk this job a few years ago when these photos were taken. On this project, primarily glulam and CLT were used from the mass timber product list we just went through. On the left, you will see the massive first floor glulam beams and columns. The photo on the right gives a perspective of the size of the project. While it appears from this photo that this is a 3-story project, only half of the space is 3 floors with large open spaces. The opposite side of the building where all the offices were located was built with 6 floors. On the left-hand side, you can see several unitized curtain wall panels that were placed onto the structure, and on the right, you can see the top-mounted anchoring system that was used along with the steel backpan design at the spandrel. The anchor is mounted directly to the CLT top surface at an anchor slot location, and you can also see the 2-inch concrete topping where a removable mold was used to cast the anchor slot. And you can see that the anchor plate is simply screwed to the CLT floor with multiple screws. These photos show the 20-foot ceiling height in the common areas of the structure, and you can see the glulam columns and beams as well as the underside of the CLT floor above. By code, these visually exposed wood surfaces can be left fully exposed, as we will see later in the presentation. Here you can see where the glulam beams are supported by the columns and how they tie into the perimeter glulam beams. On the right, you can see the 3-ply CLT floor along with the steel pour stop for the concrete topper. On the left, you can see the gray weather barrier membrane capping the end of a 5-ply CLT roof. This is what the building looks like today. At first glance, you would not know this is a mass timber building. That is until you walk through the doors. This is a key point to notice. Mass timber buildings often use more traditional glass and aluminum framed exteriors. This will become important as we discuss testing toward the end of this presentation. From the very first mass timber structures built in North America, this chart shows how the number of these projects have increased over the years and where they predominantly exist. As of June 2023, There are a total of 1,860 multifamily, commercial, or institutional mass timber projects in the United States that are either in progress or have completed construction. Keep in mind, the first major structure in the United States was built in 2016, and this is when the proliferation of mass timber projects started escalating in the U.S. Now we will talk about various large-scale projects that have been constructed in the U.S. and abroad, and as well, we will also show the largest project plans that are currently being looked at throughout the world. The image here is of the Cleveland Intro project in Ohio City, Ohio. Just across the iconic Hope Memorial Bridge from downtown Cleveland is seen here, sometimes called the Guardian Bridge, which is, of course, the namesake of the Cleveland Guardians. This building was finished in 2022 and is located across the street to the south from the famous West Side Market in Cleveland. Standing at 130 feet in height and having a massive 653,000 square foot under roof, this project is not the tallest in the U.S., but it is the largest mass timber building in the world currently. It is 9 stories in height, having 7 stories of mass timber built over 2 stories of concrete podium, and provides space for both commercial and residential occupancy. Shown here are a couple photos that were taken in February 2021, and you can clearly see the glulam columns and beams, as well as the 7-ply CLT floors used on this level. Below, you can see the concrete-based structure. This building services residential and commercial tenants and is finished and occupied as of April 2022. This project is the Ascent project in Milwaukee, Wisconsin. The Ascent project is 25 stories tall and stands at 284 feet. This height makes this structure the tallest mass timber structure in the world currently, but that will not last for long. It is quite interesting to me that both of these projects exist in the upper Midwest and not on the West Coast, as you might think. The tallest proposed projects in the U.S. currently include the SPAR project in Portland, Oregon, which would stand at 299 feet in height and would have 48 stories. The next is the Timber Towers project in Philadelphia, which would stand at 62 stories in height. The tallest proposed structure in the U.S. currently is the River Beach project in Chicago, Illinois, which would stand 748 feet in height and would have 80 stories. The tallest mass timber projects in the world that are currently built, besides the Ascent project in Milwaukee, include the Hout residential project in Amsterdam, which stands at 240 feet and 21 stories and was built in March 2022. Next is the Hoho Tower in Vienna, Austria, standing at 276 feet and 24 stories and was constructed in December of 2019. And the Mjørnstena Tower in Norway, which stands at 279 feet, 18 stories. It was completed in March 2019. The Ascent project stands taller than all of these at 284 feet, a mere 5 feet taller than the Mjørnstena Tower in Norway. The tallest proposed projects in the world include the Oakwood Tower in London. This structure would be amongst the tallest buildings in downtown London, standing at 1,000 feet and 80 stories. Finally, the tallest proposed project in the world is the W350 project in Tokyo. This project, when completed, would stand 1,148 feet tall and cover 70 stories. The plan is to have this project completed by the year 2041. Now let's switch gears and talk about major code changes that took place between the 2018 IBC and the 2021 IBC that spurred much of the mass timber frenzy that we see. Shown here is Table 601 in the 2018 IBC, which highlights the required fire resistance ratings for building elements for all 5 types of construction. You will see here that in this section, that would be used to address mass timber construction for any jurisdiction that is using the 2018 IBC or anything before 2018. The major item to note here is all types of construction have an A and B group under the type, except for type 4. Type 4 shows only one header, and that is the HT, which stands for heavy timber. It is important to note that there is a difference between heavy timber and mass timber, in that mass timber is more representative of a true building type, whereas heavy timber is more relevant to a material type that is set aside for type 4 structures. The code references here represent the entirety of CLT reference in the 2018 IBC code. In Chapter 6, there are 2 references for different types of materials that can be considered under Type 4 construction, and surface covering materials that are required to be placed over CLT. Chapter 7 addresses the calculation of fire resistance for visually exposed wood members and wood decking, but it does not mention mass timber elements by name. The rest of the references in Chapter 23 are simply specifications on minimum thickness requirements when CLT is used in specific applications. Switching now to the same table in 601 in the 2021 IBC, you can see there are some major changes. No longer is Type 4 the only construction type that doesn't have 2 subtypes under the Type 4 header. Now there are 4 subtypes to include types A, B, and C, along with the HP designation that already existed. However, with that said, mass timber construction is not limited to Type 4. That is simply a dedicated building type for a complete mass timber project. In fact, you could find mass timber projects within this entire window of building types. One major difference between types 4 and other types is that the horizontal separation requirements for all type 4 construction are 2 hours. And in types 3A and 5A, for example, the minimum requirement is 1 hour. Proposed changes added types A, B, and C to the height tables and allowable stories. With the changes, Type 4C can be built to 9 stories at a maximum of 85 feet. Excuse me, I've got a phone ringing in my room here. With the changes, Type 4C can be built to 9 stories at a maximum of 85 feet. Type 4B increases that maximum height to 180 feet and 12 stories. Finally, Type 4A allows heights up to 270 feet with 18 stories. The maximum allowances are contingent upon the occupancy type. These listed here are the maximum allowable for qualifying occupancy types. The first major proposed change set the requirements for the allowable visual exposure for each of the new types of mass timber construction. The tallest of the group, Type 4A at 270 feet and 18 stories, requires that all walls and ceilings must be fully protected, and the finished floor must include a minimum 1 inch of non-combustible material in conformance with Section 804 of the code. Type 4B at 180 feet and 12 stories allows for up to 20% of the ceiling to be visually exposed, or an equivalent of 40% of the floor area to be allowed to be visually exposed on walls or columns. So if you have 1,000 square feet of floor space, 200 square feet of ceiling, or 400 square feet of wall surface can be left visible. You can also have a combination of floor and wall visually exposed as long as it follows the mixed unprotected area exposure formula in the code. The floor must be protected with a non-combustible topping as it is in Type 4A. Type 4C is much simpler. For any structure 9 stories or less and 85 feet or less above grade, there is no requirement for any surface to be covered. You can leave walls, columns, ceilings fully visually exposed. The floor finish is not required to be non-combustible, but must be in compliance with Section 804 from the code. From the new allowances in the code, we understand that there are code-compliant conditions that allow for wood surfaces to be completely visually exposed. We also understand there are situations where code compliance requires that the surface be protected. Logically, it follows that in order to develop a good test plan, there really needs to be a fundamental knowledge of the material you're working with, how it behaves as a construction material, and more importantly, how it behaves in a fire. In the next few slides, we will look at some of the fundamentals on how wood behaves. As we all know, wood and fire are not exactly good partners, as this poor lighting structure dramatically displayed, unless it is intended for warmth or outdoor cooking. But what about when we really don't want wood to support a growing fire? The first lesson, wood is good, but strange. I cannot take credit for this statement. Back in 2009, Dr. Joe Lestibrick, one of the premier building scientists in North America and principal of Building Science Corporation, wrote an article with this title. It is a fascinating article and one that I highly recommend reading. In his leading statement, he said, if someone invented wood today, it would never be approved as a building material. It rots, it burns, it has different strength properties depending on its orientation, No two pieces are alike, and most cruelly of all, it expands and contracts based on relative humidity. I'll summarize some of what Joe wrote in his article, and it will discuss what happens when wood is warmed, when it is exposed to humidity, and why this is important both from an architectural standpoint as well as a fire protection standpoint. In addition, we will look at answering the following questions. What about wood makes it combustible? It almost always has a considerable amount of water within its cellular structure. Isn't that a good thing? What are the differences between mass timber when compared to more traditional construction? How does it compare to wood framed construction? How is fire resistance calculated in CLT floors and walls? How does it hold up structurally as the wood is consumed? Doesn't it lose strength? Finally, in this section, we will ask the question on what aspects of wood make it a good construction material, considering its natural combustible nature. So let's look at wood and why it is good but strange, and we will start with its relationship with relative humidity. Wood is hygroscopic, which basically means moisture content in wood adjusts to atmospheric changes in relative humidity. I will be saying relative humidity a lot, so from here on out, I will call it simply RH. This chart is called a sorption chart, and it shows the moisture content range in wood at various states of RH in the atmosphere. The two vertical red lines represent the typical interior RH levels in wintertime, low end, and summertime, high end. And of course, this varies among different climate zones. You'll notice that equilibrium moisture content can cycle between 4% and 12% seasonally under typical conditions. It also shows the relationship is fairly linear until about 70% RH, and then it really climbs. Why is this important? Well, if you're an architect, you may want to understand how this can affect the dimensional stability of the wood. Wood expands at a much higher rate perpendicular to the grain than it does parallel to the grain. This means if you're using dimensional lumber framing and RH increases, the length of the stud will not vary much, but they will get wider and thicker. Fortunately, with engineered wood such as CLT, the fibers are oriented perpendicular with each successive laminate layer, and this does create some stability in this regard. If you are a fire protection engineer, however, you may be less concerned about dimensional stability and more concerned with moisture content, in particular lower moisture content. If you've ever spent time in a thermodynamics class, you know what this chart is. For those of you who have not seen this before, this chart is called a psychrometric chart. This conglomeration of straight and curved crisscrossing spaghetti lines you see here is very simply used to show the relationship of how much moisture air can hold at any given temperature between 30 degrees and 120 degrees Fahrenheit. Most everyone has a basic knowledge of RH, which is reported as a percentage. But we know instinctively if you are in Houston, Texas, and the RH is 80%, that you are going to be sweating like crazy and will have a bad hair day. Conversely, if you are in Phoenix, Arizona, and the RH is 10%, we better bring the chapstick, and you will quickly realize that static electricity discharge can be quite painful. Looking at this chart, the bottom horizontal axis represents the zero moisture line, or 0% RH. The curved upper axis represents saturation, or 100% RH, and the curved lines in between are RH percentage lines. The vertical axis on the right represents the mass of water in 1 pound of dry air for any given RH and temperature. Let's say you have a stack of lumber and it is at equilibrium and the temperature is 60 degrees at 40% relative humidity. The red circle indicates the location of those stated conditions on the chart. If the temperature during the day rises to 80 degrees but no more water is introduced in the air, RH drops to 20%. As wood comes to equilibrium with 20% RH, it will give up moisture and it will shrink as it warms. In this way, it is unlike most other building materials that will typically grow when they are warm. But keep in mind, for the sorption chart, the wood in this environment would have an equilibrium moisture content of between 3 and 5% at 20% RH. Now, if moisture is introduced into the atmosphere, for example, by evaporating bodies of water in close proximity, and the RH stays at 40%, the wood will neither shrink nor expand. Even though the warmer air has moisture, because the RH stays the same, you will have no changes in dimensions. What you will have is a moisture content rising to between 6 and 10% or a 100% increase. Okay, so wood dimension responds differently than other building materials because it is affected by changes in RH instead of temperature. That is important to know in the designing of wood for use in buildings, but no less important to the fundamentals is the understanding how and why wood burns. Let's start with the why. Wood is comprised of two essential elements. First is water. Wood will always have some level of moisture because it comes into moisture equilibrium with the environment. Fresh cut lumber can have moisture content as high as 2 times the mass of dry wood. After wood is dried for lumber, the normal moisture content lies between 8 and 25%. Of course, water doesn't burn, so we look at the dry wood component. Here is a highly magnified section of wood that shows the capillaries, or for any Canadians in the crowd, capillaries, that make up the core of the wood. This is what makes wood relatively light in weight, but extraordinarily strong. It also shows how wood transfers water from the ground roots up through the heights of the tree through the capillary action. Dry wood has about 4 to 10% mineral content, but these are not what make wood combustible. In fact, this is essentially the ash remnant after the wood has burned. Now we're talking organic polymers. That sounds combustible, and it is. This is the core combustible material found in wood. These polymers are comprised of lignin, which is about 18 to 35%. Lignin is the kind of glue that holds everything together. Then the cells are made of hemicellulose at about 25 to 35%. And then finally, cellulose, which makes up about 50% of the dry wood. Very simply, hemicellulose and cellulose are sugars, and sugar is quite combustible. Let's look at some other materials and how they compare when they are exposed to fire conditions. Concrete is very simply a massive material that absorbs a ton of heat. None of the components that make up concrete are combustible, and the biggest concern for concrete in a fire is explosives falling if the moisture content is too high. Concrete does exhibit some expansion with heat, especially if there's steel embedded in the concrete, close to the heated surface. Gypsum wallboard is a very interesting material. The way gypsum works and why it is an excellent material for fire protection is that the gypsum or calcium sulfate molecule has water molecules chemically bound to it in its natural form. It is dry to the touch, but when exposed to heat, gypsum will release the water molecules in a process called calcining, and the released water will convert steam, which cools the assembly close to the boiling point of water and well below cellulosic ignition temperatures. The calcium sulfate is a non-combustible mineral base. The water molecules serve as a bit of a binder, so when they are gone, the gypsum is essentially powder that has little to no structure. Steel expands fairly rapidly as it heats. Steel will retain a significant portion of its strength up to about 1,000 degrees Fahrenheit, when it will start to exhibit plastic deformation when under load. This is why fire test standards for testing fireproofing materials use 1,000 degrees Fahrenheit as the failure criteria. Steel melts at about 2,600 degrees Fahrenheit. Dimensional wood has been used as a framing material for years, but the frame is encapsulated by various materials, usually gypsum wallboard, to provide the fire-resistive element. Conversely, mass timber surfaces will ignite at around 500 degrees Fahrenheit and start to produce char. The base char rate for CLT, per the National Design Specification for Wood Construction, or NDS, is 1.5 inches per hour. But for design purposes, the effective char rate is used, which ranges from between 1.8 and 2.2 inches per hour, depending on the thickness of the plies. When designing for load bearing with mass timber, you always want to end up with enough wood to carry the design load after the prescribed fire resistance time has elapsed. When you are designing for fire resistance with mass timber, you start with the design load, and then you use the char rate calculation tables in Chapter 16 of the NDS. Here's an example on how this may be calculated using CLT with 1 3/8 inch plies. Say your design requires 3 plies of wood to maintain the design load, and you have a 2-hour rated design requirement. NDS Chapter 16 indicates that the effective char rate of 1 3/8 inch ply CLT is 1.9 inches per hour. 1.9 inches times 2 hours is 3.8 inches. And you can see we are well into the 6th ply at this point. At the moment, we have calculated that we need 3.8 inches of effective char coupled with the 4 1/8 inch thickness to hold the load. So we are at 7 15/16 inches. 7 15/16 inches divided by the ply thickness of 1.375 is 5.76 plies. So we've calculated we need 6 plies, but remember from the CLT discussion, CLT is only manufactured in odd ply numbers, so we actually need 7 plies to meet this design criteria. So why should we use wood if it burns? It's a good question. For starters, wood burns in an ablative process. This photo very clearly shows this glue lamp beam on the left is untouched and the one on the right has obviously seen fire, but yet the core of the beam looks identical to the one on the left. Wood first forms a char layer, which is essentially all carbon mixed with the minerals intermixed. The carbon layer is solid, but it has lost much of its structure. The carbon then burns away, leaving the minerals or ash that has no structure. The ash falls away or sloughs away and to reveal the new char layer below that has already started as it supports combustion. But as well, the virgin material below is still protected. This process repeats, and this is what we call an ablative process. There are essentially three stages of wood burning. The first stage is when smoking is called the smoking stage, when the wood begins to lose its moisture. Some will be lost to the fire, other moisture will be driven inside, which preserves the core virgin wood. CO2 is released, and this process happens until the wood temperature is about 400 degrees Fahrenheit. The second stage is called pyrolysis stage. This is when you have the realization that your campfire is burning on its own. Pyrolysis is the conversion of the combustible compounds in the wood to volatile gases, and this is what supports the flaming and further breakdown of the wood. This happens between 400 Fahrenheit and 850 Fahrenheit. The final stage is called carbon burn, and this is where the carbon is turned into carbon dioxide and carbon monoxide, leaving nothing but the ash or any other char or virgin wood that may be involved in other stages at any given time. When we look back on these behaviors of wood, what does it all mean? How can we use this to understand how to properly fire stop? Well, we use this information to carefully consider how we approach fire stopping penetrations and joints. Should we include protection within the annular space in a way of insulation? Can we use point contact? How is the mass timber assembly going to behave differently than a concrete slab or a gypsum wall? Should we protect the assembly or leave it fully visually exposed? In other words, we actually still have a lot to learn. So all of this is interesting, but how do we apply what we have learned to testing penetrations or joints for that matter? Well, in putting a test plan together, the first thing we had to discover for ourselves was how long of a duration we could expect. We know how to calculate fire resistance per the NDS, but practically speaking, we needed to know that when a fire was going to start peeping through the assembly. How long will it last unprotected? Well, this is important to know because sometimes ceilings do not require protection. How much additional time can we expect when adding a layer of gypsum wallboard to the ceiling? Again, this is important because some ceilings do require protection. What types of penetrating items would be good to analyze in determining how we might do things differently with CLT versus the concrete floor assembly? Finally, how do we push the limits of these test assemblies successfully? Like all good plans, you have to know where to start. Recently, we ran some fire tests on 100 millimeter 3-ply CLT floors. To start, we wanted to understand how long this assembly without protection would last under fire exposure for the ASTM E119 time temperature curve. The photo on the left side is the slide of the slide shows the underside or the exposed side of the CLT floor. The right side shows the top and exposed side of the assembly. You'll notice that there are pads weighted down with steel blocks and wires leading out from under the pad. These are the thermocouples that are used to measure the unexposed surface temperatures as the fire test is proceeding. The end of the test was marked when we noticed flaming on the unexposed surface at 90 minutes into the test. The maximum surface temperature rise was only 199 degrees Fahrenheit, which is a full 126 degrees lower than the standard allows. That goes to show you the excellent thermal resistance of CLT. The flaming occurred on a seam between the CLT boards on the top ply. It may be difficult to see, but look for the light orange glow at the center of the red circle. The center photo shows the flaming at about 5 seconds after the flame first appeared on the unexposed side. And this is a photo of the assembly as it's being lifted off the furnace. As you can see, it is fully involved and you're seeing every stage of wood burning. The ash has already fallen into the furnace or floor, so at some point, carbon burn was complete. You also have carbon burning. Pyrolysis as well as smoke stage burning is occurring on the top surface. This is a graph of the thermocouple data on the unexposed side. The two curves indicate the maximum temperature on the unexposed surface, that would be the blue line, and the average temperature of all 5 thermocouples depicted by the orange line. The temperature rise was fairly linear until about 71 minutes into the test, when the rate of temperature rise began to increase. This was likely when the third ply began to char, culminating in the failure of the assembly 21 minutes later. This graph shows the temperature as measured in the furnace compared to the E119 time temperature curve. The orange line is the E119 time temperature curve for assembly 1 test. As you can see, there was a deviation in the furnace temperature that began around 45 minutes into the test. This is likely due to the ablative nature of the wood when wood burning, and when the char had sufficiently attacked the first adhesive bond layer to cause delamination. This exposed a fair amount of slightly charred underlying wood immediately. Immediately afterward, the wood from the second ply became involved, and the heat generated by the fresh wood outpaced the heat energy from the furnace fuel, causing this deviation. So between 45 minutes and roughly 80 minutes into the test, the furnace gas was shut off and the furnace temperature was driven by the fuel from the CLT. Internally, we call this secondary flashover. Since the unprotected assembly only passed 90 minutes, it was decided to run a second unpenetrated assembly with a single layer of 5/8 Type X gypsum wallboard mounted to the underside. The photo on the left shows the exposed side of the test assembly, which shows the screws securing the wallboard, which were spaced on a 12-inch by 12-inch grid. The photo on the right shows the unexposed side of the assembly prior to the test, and it was fitted with 5 thermocouples in the same locations as the first test. The end of the test was marked when we noticed flaming on the unexposed surface at 128 minutes into the test. The maximum surface temperature was only 145 degrees Fahrenheit, or 180 degrees lower than the standard allows. With the addition of the gypsum wallboard, there was a significant improvement in the thermal resistance of the test assembly. Prior to failure, wood resin was seen bubbling to the surface. Shortly after this occurred, charring could be seen at the seam between the top ply boards, which then ignited within seconds after this photo was taken. This is what the assembly looked like as it was being lifted off the furnace, and you can still see remnants of the gypsum wallboard hanging on at the perimeter. This is the graph of the thermocouple data on the unexposed side of assembly 2. The two curves indicate the maximum temperature on the unexposed surface in the same manner as they were charted from the first assembly. The temperature rise was fairly linear until about 107 minutes into the test, when the rate of temperature began to rise and began to increase. And interestingly enough, the difference between the time rate started to increase until the point of failure was identical to assembly 1 at 21 minutes. The temperature rise data between assembly 1 and assembly 2 were then analyzed and compared in order to determine the fire resistance benefiting from adding the single layer of gypsum wallboard to the underside of the assembly. The data showed that according to the single layer adding the single layer increased the fire resistance of the assembly by 38 minutes. Table 722.2.1.4 in the building code provides a table of fire resistance times assigned to various finished materials when applied to exposed side of assemblies. Care to guess what time is assigned to 5/8 Type X gypsum wallboard? 40 minutes. So from these experiments, we are offered evidence to support a couple conclusions. First, the predictability and repeatability of burning CLT assemblies seems to be very consistent. Second, the finished materials table in the code appears to be very reliable as a source in determining what finishes add to CLT assemblies from a fire resistive standpoint. And while these experiments are not a large data set and firm conclusions cannot be drawn from them, it is refreshing to see that they do not contradict performances of expectations of performance. Not surprisingly, the furnace data showed a similar result from the first assembly with an almost identical deviation in both magnitude and duration. It's just shifted 41 minutes from when the deviation occurred from the first assembly to that of the second assembly. Most everyone that has been through the basics of Firestop training has learned how to identify specific systems in the UL directory and what the various alphanumeric characters mean. So I'm not going to spend a great deal of time on this, but just as a refreshment, here is an example. CAJ system CAJ 1464 has 3 definitive sections that each have a meaning. UL has done a nice job with the cataloging system, so you know by system name specifics as it relates to the assembly and the penetrating item. At this time, other testing and listing agencies use a different convention that does not identify substrates or penetrating items by the system name, but they do have listings. First alpha group indicates the floor, wall, or combination of floor and wall. So immediately you know the orientation as vertical or horizontal. In this case, C would indicate that this system can be used for a floor or a wall penetration as it is a combination system. The second alpha group indicates the type of construction that is penetrated. In the case of CAJ 1464, it is a minimum 5-inch concrete floor or an 8-inch concrete or masonry wall. The first number in the numeric section identifies the type of penetration. In this case, the system identifies this as a metallic pipe, conduit, or tubing penetration. In the case of CLT penetrations, UL has used the same system identity convention by assigning new assembly parameters to the middle alpha group. The first alpha group is unchanged, so C still stands for a combination floor or wall penetration. The second alpha group is the only difference. UL has assigned the letters G for CLT floor assemblies and O for CLT wall assembly. The numeric system remains the same as before. So in this case, a similar system to TAJ 1464 might be CGO 1464. And from that, you can identify that you have a floor or wall penetration through CLT with a metallic pipe, conduit, or tube. There will be some differences you will notice with CLT penetration listings, and some things will be familiar. CLT listings will have the following requirements at a minimum. First, any approved CLT assembly must be manufactured in accordance with the ANSI APA PRG 320. This ensures a minimum standard of quality for the CLT that is approved for these systems. Next, the slab thickness will be designated as a minimum, which is familiar. One difference, because CLT is a laminate material and fire resistance calculations have a dependency on ply thickness, both the number of plies and ply thickness will be specified as a minimum. Finally, any protection that will be required or in some cases optional will be listed as such. These protective materials will typically be gypsum wallboard, at least as we get out of the gate. We're happy to state that STI has 12 relatively new listings with Intertech as shown in the table on the right. Among the penetrants we have are 4-inch PVC and ABS pipe, AC line sets, cable bundles, metallic pipe, insulated metallic pipe, and blank openings. Some nice features of our listings include optional protection for CLT floors, having a minimum thickness of 4 inches with 3 plies for 1 hour or 6-inch 5-ply for 2-hour rated systems. These systems can be located both in the Intertech directory of building products and on the STI website Firestop System search page. You might be wondering, can you test a perimeter fire barrier system with CLT? And the answer to that question would be absolutely yes. STI has released one system already, and we will be releasing 3 total CLT perimeter fire barrier systems in the very near future. Intertech, through Intertech, and we have plans to continue with more tests this year. Here you can see an example of our first test assembly for perimeter fire barrier utilizing CLT. The first thing you'll notice here is that there's not a protective membrane on the ceiling. Other systems that have been tested require the user to not install 1 or even 2, but 3 full layers of 5/8 Type X gypsum wallboard at the ceiling. And while that is a safe measure, it certainly doesn't provide the benefit of the biophilic design that we discussed at the start of this presentation. You know, the one where one of the major draws of building with mass timber. Also, testing with no floor covering means all code acceptable options for floor toppings are on the table. In other words, if you have a type 3A or B structure with mass timber, type 4, A, B, or C, or type 5, you can want to have that beautiful wood grain showing like most owners and occupants will want. You will only have to reach out to SDI and we'll be glad to work with you. While we're at it, there are a few more feature benefits that these systems will showcase. Shortened raised spandrel valance back pans that will allow you to go as tall as you want, but you can get down to 8 inches for full floor to ceiling glass systems. Up to 8-inch wide joints. While joints in mass timber construction rarely go that wide, SDI does have it covered in the event that it does. Unitized or field installed system capable. Structural silicone IG glazing or preferred gasketed pressure plate glazing. Optional weather resistant joint seals. Optional alternative insulations below the back pan, and in the event the additional thermal protection is desired. Optional floor toppings in conformance with the requirements. Optional spandrel covering materials. Optional wall elements including kiss mullions, wind load anchors, intermediate transoms, architectural cover plates, thermally broken back pan design, hybrid window wall applications, and there are more to come. There are some excellent online resources to learn about mass timber construction, which include the following. Woodworks organization, or woodworks.org, is an amazing reference for all things mass timber, including structural, environmental benefits, as well as fire protection. American Wood Council would be a source where you would locate the ANSI NDS 2018, where Chapter 16 refers to the calculations for determining fire resistance of mass timber elements. The Engineered Wood Association is where you would access the ANSI APA PRG 320 document, and that download happens to be free of charge. There are many other sources, but these three have amassed a significant amount of information that is available for further education in mass timber. And finally, a fascinating website to nerds like myself who want to learn more about how wood behaves, among many other things, the Building Science Corporation, which includes a massive library of building science-related training and articles that are all available at no charge. In conclusion, I'm extending a thank you to Dr. Joe for his excellent source for all things related to building science and his article on how wood is good but strange. We learned that wood is hygroscopic, so it accepts and rejects water based on ambient conditions, and as a result, changes in dimension. But most importantly for fire protection, moisture content. Wood is ablative, and so that makes it a good material for fire-resistant construction. You just have to design char depth into the calculation for fire resistance. PRG 320 is the minimum requirement of quality standard that can be used for fire stop listings. We really have to reimagine how we approach fire stopping in CLT. Metallic penetrations may offer new challenges that are not present in other types of construction. When fasteners are used for protective layers or devices, they must extend into the wood that would be uncharred for the desired rating. Point contact systems will be a struggle to achieve, but we at STI will always push for that envelope. And finally, insulating against radiative heat will be key in some systems, and this really ties to the limited point contact difficulty. That is all I have for you today. I hope the presentation was as fun for you as it was for me, and hopefully you are walking away with some new knowledge that you didn't have before. Thank you for attending.
All right, Tim, very good. And Anna, if you are ready, we're going to launch a poll to see how well everyone was listening. So if you're ready, you should see the poll up there. We'll read through the questions. Question number 1, which of the following materials is not considered mass timber? Would that be cross-laminated timber, rough-sawn wood beams, mass plywood panels, or glue-lam beams and columns? So which one is not considered mass timber? All right, moving along. Number 2, which version of the IBC saw the most dramatic change as it relates to mass timber? Was it 2012, 2015, 2018, or 2021?
Hey, John, just real quick on that.
Yes.
Just to make sure that people understand that question, it is the one that it changed to, not the one it changed from.
Okay, yes. Thank you, Tim. And Tim, do you realize that you can't spell timber without Tim? All right, so which did it change to? So we're changing to, which was the biggest drastic change. Okay, that's question number 2. Thanks for clarification, Tim. All right, number 3. What is the unique burning characteristic of wood that makes it a good material for use in mass timber construction? Is it because it's an ablative material? Because it's kiln dried, so it doesn't smoke much? Is it hygroscopic material? Oh, wait, I just heard you say that. And it contributes to the, geez, Tim, why don't you read these questions?
Biophilic design.
Yeah, that, exactly. All right. Make your selection now on number 3 there. I'm definitely getting that one wrong. All right, number 4. Where can you find the formulas to calculate the fire resistance of mass timber elements? This was actually someone's question in the lobby right now. So is that going to be the ANSI PRG 320? Are we looking at the 2021 International Building Code? Is it the ANSI AWC NDS? Or is it the UL Fire Resistance Directory? All right, where can you find those formulas for your calculations? And finally, number 5, where is the tallest mass timber structure currently being proposed to be built? Is that beautiful Milwaukee, Wisconsin, Tokyo, Japan, London, or someplace in Norway? Tim's got these great answers, things I can't pronounce. I love it. All right, so finish up your test now, and then don't forget to hit submit, and we'll see how everyone did. All right. Anna, close it out whenever you're ready. And then we will, Tim, if you could roll on to the next slide there. You might have to X out of the poll up there.
Okay, I do have to X out of the poll. 1 second.
Yeah.
Okay.
And then you'll get control.
There we go. Whoops. Back. Sorry.
All right. We'll just see how everyone did real quick. Number 1, which of the following materials is not mass timber? Rough sawn wood beams. That's correct. 75% of you got that one right. Which version of the IBC saw the most drastic change? And we were changing to 2021. So 62% of you got that right. 28% of you got 2018. So might have been a little bit of a trick question, but Tim tried to wink at you there. Number 3, what is the unique burning characteristic? It is an ablative material. So 49% of you got that one right. Number 4, where can you find the formulas to calculate your fire resistance of mass timber? And that's going to be C. 47% of you got that one right. That's the ANSI AWC National Design Specification for Wood Construction. And then finally, where is the tallest mass timber currently being proposed to be built? And that is Tokyo, Japan. 53% of you got that one right. So great job, everyone. We do have a few more minutes for your questions to Tim, so we'll roll on over here. And please, like we always do, if you like the presentation today, grab your phone, click that QR code. We give some swag bags away. We pick some random winners. So if you enjoyed today's presentation, let us know how we did. And Tim, we have some questions for you here.
All right.
All right. First question is from Bridget. Are all penetrations for MEPs made during fabrication, or are any penetrations made in the field?
It's a good question. There's a lot of times the mass timber elements will show up on the job site to be installed that are already pre-cut with openings. But when that is not done, it can be done in the field as well. So the answer to your question is that's done both ways. But I think primarily the design would incorporate having the mass timber elements pre-constructed with openings.
Makes sense. Almost like cast in place devices for your concrete there. Mm-hmm. All right. Next question here. This is, can the outer layers that have been charred be replaced, assuming the internal layer maintains its strength? I'm guessing in the event of a fire, you're probably going to want to replace the whole thing, correct?
Yeah, anything that you're charring, if you've eliminated a portion of your fire protective element, that would necessarily need to be replaced so that you're bringing back that fire resistive element and keeping the structural capacity.
Daniel asked the question about providing the equations for calculating the char layers, but I think question number 4 answered that. But he had a follow-up question: are the char layer calculations the same for columns as well as horizontal assemblies?
It's a good question. It's probably a little bit different. It doesn't really delineate that, as I recall, in the NDS. The NDS is a document that you can purchase It is not something that is it's available free of charge, but you can purchase that, and it does have those calculations inside of that, and it gets a little bit involved, but I think the char or the effective char rates that I shared with you in the presentation were primarily meant for mass timber elements like CLT. I don't know. I don't think they really applied to, say, glue lam or something like that.
All right. Thank you, Tim. So if water is sprayed on a timber building to put a fire out, is the building compromised? I'm sure it is in some way. I mean, I guess maybe the question is, do you have to replace the whole thing, or maybe just part of what was burned?
I think you're going to probably need to you're definitely going to need to replace the part that was burned. Kind of in response to the same question earlier. But as far as spraying water on wood, I think it probably depends on how it responds to that. I mean, if you do see some changes in dimension or whatnot, you could see something like that. But I think that's one of the we'll wait and see kind of things. So hopefully we never see fires in mass timber structures, but that will probably be something that will be either decided on with each application.
All right, great. We are at the top of the hour here, Tim. So we have a few more questions for you, but we'll get those to you offline. If you could just scroll to 2 more slides ahead. To the Access STI slide. This is where people are going to need to get an Access STI account if you don't already have one. So grab your phones and download this QR code again. Get yourself an Access account. Once you do, in that dashboard, you'll find Firestop University. Just give us about 3 to 5 days. We'll get your certificates. A recording of this webinar will be up there, as well as a lot of other courses that we have available for you. So again, this is free of charge. It takes about 2 minutes to create your account. And then once you're in that dashboard, find Firestop University, and that's where you'll be able to find your certificate after this. Anna, we're kind of over time, so maybe why don't we just tell the people, Tim, scroll all the way to the end. Go all the way to the badge. There we go. There it is. Anna, what else do we need to tell them?
Just want to remind everyone that we will be reporting AIA credits for those who gave us their member number and attended at least 75% of this live webinar. If you have an AIA number and did not give it upon registration, please send it to webinars@stifirestop.com. And lastly, you will all receive an email within 5 business days when the recording and certificates are ready. If you have not created an Access STI account yet, please make sure to use the same email address you used to register for today's webinar when creating your Access STI account. That's it. That's all I got, John.
That's it. All right. Great job, Anna. Great job, Tim. Thank you for your time, and thanks everyone out there. You want to say goodbye to everybody, Tim?
Yeah, thanks for attending, everybody. I really appreciate the time that you spent listening, and if you have any questions, don't hesitate to reach out to me. You can do it through John or Anna or whatever, but just send your questions direct to me.
All right. Take care, everyone. See you on the next one.
All right. Bye-bye.